4. I'm a genius.
Okay, let's see what your score is. You made it to 72. So congratulations, you qualify for the fun thing. Now here's the story behind the fun thing. We're going to go to the Science versus Math group on Facebook. And a friend of mine has posted something really cool that his parents did. His parents were early filmmakers who posted a whole lot of really cool science and math videos. And he went back and he started posting. One of them is from 1959. You know how long ago that is? I think we need a calculator.
Oh, I know how long ago that is.
It's 2014 today minus 1959. You think you can figure it out on a calculator?
Yeah.
2014, that's this year.
So I'm really clear all.
While you do that, I'll go load up the video.
2, 0, 4, 1, 4. 2014 minus, what is it?
1959, I believe.
1959 equals minus
minus 7,145
so that's
years.
BC.
No, I think you did it wrong. 2014, it's a 4-digit. I think you punched in a 5-digit number at some point. 2014 minus 1959. Right,
I did do that.
55 years ago. So this is like a lifetime ago, pretty much.
Nah.
These folks who were friends of mine, parents of my friends Scott and Eric, they made this great video. And it goes like this. It's called, hold on, I'm having all kinds of Windows crap happening here. I hate Windows. This is called the Seven Bridges of Königsberg. And we're not going to watch the full video yet. We're going to try and see if we can figure this out from ourselves. In a city called Königsberg, there are 7 bridges. You see how there's water, and there's a little water thing here? This is Königsberg. And you see how there's 7 bridges? 1, 2, 3, 4, 5, 6, 7. The question is there any place you can start in Königsberg, like they start there, and then cross over each bridge just once? Is there any way you can do that? So for example, you think so?
Yeah, because you can.
Yeah. And then let's see where they go after this. Oh, there they didn't cross the bridge. They went to the other bridge. Now watch what happens. They go over here. Now they cross that one. But look.
Well, actually, there is because if you
But
do
look,
this,
they end up there, and then they've. But look, see, they end up there, and they've gone through all 6 of these bridges once. But look how they never went across that bridge.
I know how they can do it.
You think you can figure it out? I tell you what, I have it. Okay, I also have it drawn here if you want to draw it on paper.
Awesome.
Do you want to erase that other route, or you want to keep that route?
No,
Should we back it up?
No, it's okay. So look. From there.
Yeah. Okay, so you want? Okay, so we'll back it up. We'll back it up to where they. Let me just back it up a little bit. So you're saying right here, right here they should have gone this way, right? Right here they should have crossed the bridge this way.
No, hold on. Let me figure this out. No,
You think there's a way to do it? Should be easy, right?
No, because if you do this.
Well, you also don't have to start from there. Maybe our problem is if we start from there. We can start from wherever we want. Yeah, now you're stuck here and you've used all your bridges. The moment you burn a bridge, it's kind of gone, right? The moment you cross a bridge, you kind of cross it out. You can't cross it again, right? So far we haven't found a way.
Exit. Oh, hold on.
Do you want me to erase these lines? Back it up and erase those lines?
I need to figure this out.
Yeah, I think it would be good for you to try and think about this like as a homework problem. But we're also going to watch the video and learn how a very famous mathematician, I believe it was Euler, his name doesn't have to do with oil, like the sticky gooey stuff, that's just a German name. He figured it out. And you know how in science
Well, it's easy to figure
This is
out.
actually a mathematical problem, and let me explain the difference. In science, we look at how something behaves, like stars in the sky or rocks, and we try and figure out how they work, right? So we design experiments, and we come up with theories that fit the facts. You know that science versus universe game? Like, you know the colors one that you made? You know how the universe works. Don't say what it is, because there's people out there that may be playing this. So you know how the universe works. You developed a game, right, where people have to guess your rule. You know the rule. No one else knows the rule.
Hold on. I need
Next.
to delete this.
No, you don't.
It said X.
Okay, we'll deal with that in a second. So, if you're the universe, you kind of have a secret recipe for how everything works. And what a scientist has to do is come up with experiments and theories saying what may or may not work. It's different in mathematics, and here's how it's different. In mathematics, we know everything about the problem. There's no surprise thing like, oh, a supernova might solve this for us, or something weird like that. Here it's a mathematical problem. So we can look at this in mathematical terms.
Okay, and eventually you'll get it because...
Okay, we'll pause the video and come right back. Now, this was a puzzle. This was a puzzle that the people in mathematicians and the people in Königsberg, this is a very famous problem of the time. I guess probably the 1700s. This is like 300 years ago. Nobody could figure it out.
I could figure this out.
Do you think it's possible or not possible? You think it's possible? My homework problem will be for you to find a way to do it. But I'm going to show you how Euler figured it out. What he did was, he looked at this a little bit differently. He said, look, there's 4 places where you can start or finish, right? There's 4 land masses, right? So really what you can do is you can draw on a sheet of paper those 4 land masses as places you can go, right? Let's call them nodes or vertices. In a mathematical sense, we don't have to think of them as land. We can think of them in a more abstract way. The bridges are connections between these 2. So you see how we have 2 connections between 1 and 2, right? Here and here, we have 2 connections. We can draw these bridges like this, okay? See how there's 2 bridges? We're going to end up with 7 bridges. Can you tell me what I have to draw between to draw that bridge? That draws between what and what? What land? I'm going by the numbers now. What landmass and what landmass?
Can we actually do this one?
Well, let's start with this one. I'm trying to go in order. So what's that one? That goes between what and what? 2 and 4, right? So we need to draw a bridge in there. Okay? Now that, what's this one?
Easy.
What's this one?
That one's...
Well, what's this bridge? That goes
it's
between
this one, 1 and 4.
1 and 4. And then what's these? Oh, we have one down here. Let's do that one next. What's that one?
From 4 to 3.
From 4 to 3. You got it right. Okay? And then how many bridges do we have between 3 and 1?
2.
Right. So we also have to draw this. Okay? Now actually a better way to draw on this is if I switch, if I put 2 in the middle. Actually, let me draw it again. I'm going to do it this way. 1, 2, 3. I'm just drawing it a little differently. Between 1 and 2 we have 2. Between 1 and 3 we have nothing. Between 2 and 3 we have 2. Then we have between 1 and 4, and this and this. Okay, so look. This is another way to draw the same thing.
I think I might have figured it out.
How would you do it?
Hold on. Let me start from here. Exit. No. Start from here. There. Head that way. Exit that. Okay. And up.
You know what? What people in the 1700s did was they tried maybe to the several thousand different combinations, and they were sure that there was a solution, but nobody could find it. Euler came around, and he had a very interesting argument that proved, in mathematics, a proof is like a theorem that is absolutely true. It is known to be true. And he proved how it is impossible. Can I show you the way it works? This is the same thing, right? We would if we did this, like let's say we started at 1, we could only use each bridge once, so we would have to find a way. The moment, like if we start in one and we go this way, and this way, and this way, then we have to go out via this way, right?
But we can't.
Then we have already chewed that one up, so we have to go this way. Now we only have 2 bridges left, and we see that if we did that, we wouldn't have a solution. He saw something really interesting. If you have a node, a vertex, that has an odd number of things on it, then, like if it has only one connection on it, then you can start there or end up there, but you can't pass through there, right? It has to have an endpoint on it, right? So if it has 1 or it has 3, what happens if it has 3? If it has 3 and you start out there, you can start out there and then maybe later pass through there, but you can't start out and end up there. And furthermore, you have to have a starting point or an ending point on if it has an odd number of connections. What about if it has an even number of connections? That would be like a 2 or a 4. This means if it's a 2, you can pass through it, but you can never start or end there, right? If it has a 4, you can pass through it once and then later come back and pass through it again, but you can never start or end there. Does that make sense? So the moment you make that observation, you realize that there has to be an even number, a node with an even number of connections cannot have a starting point or an end point. Does that make sense? And if it has an odd number of connections, it has to have either a starting point or an ending point, but it can't have both.
Right.
Does that make sense? So let's see in this graph which ones are even and which ones are odd. We'll only look at the odd ones. So how many connections does this one have? 1, 2, 3.
3.
That's odd, right? That's an O. How many connections does this one have? 1, 2, 3. That's odd too. So far we're okay because we could have a beginning point and end point there. But look at this. How many connections does this one have?
1.
No. 1, 2, 3, 4, 5, right?
Oh, 5.
5 connections. So it's odd as well, right? How many connections here?
3.
3. So it's odd as well. So we would have to have 2 starting points and 2 ending points. We can't do that. The problem is we have too many odd ones. It's okay if you have one odd one and another odd one. That's your starting and ending point. But then all the other ones have to be even. So you know what else he said? And this is really brilliant. He said all we have to do is add 1 bridge to fix this. Do you want to pick any? It doesn't matter which 2. The moment you add 1 more bridge between any 2 of these, 2 of the odd ones become even ones. And then it's possible. You want to add, well, you can't add from, it has to be between landmasses. There's 4 nodes. You can't add from a bridge to a landmass. Well, you have to connect two of these, like that and that, or that and that.
I see.
I'm going to connect that one with that one. So I'll draw it in here. I'm not going to draw it all the way around. So you want to do this, right? Now, this one becomes even, right? Because now you have 4 connections. This one becomes even because now you have 6 connections. You have to, in order for this to work, you have to start from an odd and end up at an odd. You think you can figure it out now? So wait, slow it down. Start at 1. That's your starting point. Okay, I'll put an S there for start. Which bridge do you want to go over first? That one? Okay, I'm going to cross that over. Cross that up. So you can't go over that bridge again. Now you're there. Where do you want to go? Okay, so you're going to take one of these bridges. Okay, now you're there. Where do you want to go? Good. So,
I see.
So now you're there. You're going to eventually end up there. You want to go back over this bridge? This other bridge? Because you haven't gone. You want to go back there? Okay. Now you're back there. Now look. Well, you know what? Don't do this yet because look, you haven't used any of those 2 bridges.
Oh yeah. Really?
So you have to go there, and now you're there. Now you go this one.
Yeah.
Now you're doing this one.
Now I do that.
And now you do the final one, and guess what? You've ended up at your ending point, right? So what Max just figured out is you start here, you go bing,
Mom isn't there.
and then bing, and then bing, and then, no, bing, and then bing, and then bing, and then bing, and then we had to do this to get rid of that loop, and then there, and then there. So just by adding 1 bridge, and it could be a bridge between any places, you go there. So now, looking back at that, knowing what you know now, do you think it's possible to find a solution?
No.
you want to try and work it out by the morning? So the proof has said it's not possible. But you know how you can fix it. Okay, so with that, let's watch this video because it's really cool. What are you doing? Oh, sound all the way up? I tried to do that, but it didn't do anything. Okay, yeah, we're already in full screen mode. Yeah, go back to full screen mode. Okay, so we got full volume. Well, let's also hit HD. Hold on. Too many Windows things here. So let's watch this cool video from 55. This is 55 years old. It was hand animated. Okay, let's watch this. Look how pretty those bridges are. The Seven Bridges of Königsberg.
In the 18th century, a popular amusement on a pleasant summer's day in the city of Königsberg was to try to cross the 7 bridges of the city in a continuous walk, crossing each bridge once and only once.
Think you can do it? But you see how people actually thought they could do it? They would spend all day walking and trying to do it. So look how they skipped that bridge, right? They forgot about that bridge. Oops!
No one had ever succeeded in doing it, nor had anyone proved that such a walk was impossible.
But then you stuck
You get stuck, yes. Yeah.
Leonhard Euler, a brilliant Swiss mathematician, became intrigued by the problem. He abstracted all of the land areas to points, and the bridges to lines connecting them.
This is called a graph. Want to pause?
A point, or vertex, is odd, according as the number of lines leading from it are odd or even. An odd vertex, such as these, must be the beginning of a walk. It is said that Greek mathematician Pythagoras was for the end of a walk. And one day, if all bridges are to be crossed only once, very curious.
We're getting two videos.
Same number of tiles in the two squares.
For some reason, we had this video start too. We don't want that. I was hearing two audios. So let's back it up just a little bit, and we'll do it again. So you see how here we're talking about now that it's a graph. We're looking at whether there's even numbers or odd numbers of connections going. Okay, and this is a very short video, right? We're already halfway in.
Or even. An odd vertex,
It's 2 minutes.
such as these,
Yep.
must be the beginning of a walk,
It has to be
or
either.
the end of a
It has to
walk.
be either the beginning or end.
If all bridges are to be crossed only once.
If it's an odd number, so you can only have two odd
An even
vertices.
vertex, one can go on through without stopping.
If it's even, you're going to have pairs. So you're going. It's neither an ending or a starting, but you can pass through it several times, maybe. Right?
In the 7 bridges of Königsberg, there are 4 odd vertices.
See, these are all odd numbers, right?
But a continuous line can have only 2 ends. Hence, this walk is impossible. The walk can be made only if there are no more than 2 odd vertices. If we add another bridge,
And it could be anywhere.
we have 2 odd and 2 even vertices.
And then you can do it,
And
right?
we can cross all bridges in one continuous walk.
See
Hold
that?
on, is this where I put my bridge?
Tiles in a square.
No. Let's see where you put your bridge. Let's go back and look.
Oopsies.
That's okay. You oh, you know what? You started the triangular one again somehow. Don't use the keyboard. Don't hit the keyboard because that seems to launch just.
I didn't hit the keyboard.
Yeah, let me control the video, okay? So look, let's go back to where we were. So we know that this is not possible, right? Because it's too many odd ones. So here was the fix they added. The fix the narrator adds is to add that bridge. That's right. In our diagram, that's kind of like that's kind of like adding one here. That's not the one we added. The one we added was you added another one here. So you added one right here. But it doesn't matter. It turns out it doesn't matter. You can add one bridge between any of the four masses, and that fixes the problem. Yep, hit play.
And we can cross all the bridges in
Oh!
one continuous walk.
I don't know why that.
I think.
I don't know why we keep getting the Pythagorean one loaded. The one down, this one keeps
Can we like
launching.
somehow erase it or?
No, it's on the page.
One more bridge.
I think it's, you can't hit space.
Of Königsberg.
Yeah, I think you
You
can't.
just played it.
Oh, I just played it. Alright, we're having some technical issues here. Yeah, I don't know how to get this video by itself. In any case, let's back it up just a little bit and play the ending of that.
Had there been one more bridge, one continuous walk.
So there's their solution, and now they translate that back into the actual
Right.
bridges. So he's gonna build a bridge, probably a yellow bridge. Watch. In your so you see he adds that one bridge there.
The bridges of Königsberg.
So all you have to do is add one bridge and that fixes it. So now you understand the deeper mathematical way of thinking about it, right? Yep, and then they end up there and they're done. Isn't that cool? So check this out, Max. Like we have in science, we have theories for what is right and wrong. All the universe has to do is to say, wait a minute, here's a case where your theory doesn't work, right? And then we have to improve the theory. It's not that the universe is wrong, it's that our idea of the universe is wrong. What's different in mathematics is we either see something is provable or can be proved not to be true. In this case, Euler proved that you couldn't do it. And he also said, here's all you have to do to fix it. Build one more bridge. And then people could spend all day wandering around and crossing all the bridges only once. So that's kind of a neat little puzzle, huh? You want to say goodbye to Eric Cornwell, the son of the people who made this video? Because he's going to see you figuring this out. Let's say goodbye.
Bye.
You want to say thanks for the film?
Thanks for the film.
Yeah, it's pretty cool. Thanks for the film. Yeah.
Oh,
Good. All right, thanks, guys. That was cool, huh?
Hold on.
Wasn't that fun?
Hold on. Can I see that thingy?
Oh yeah. You're going to use the concentration gun? Zap.
Alright, as you can see, this is the concentration gun. Yeah, Mom's handling crickets. I'm dealing with 250 crickets here.
Oh deal. Oh dear. He's going to get loose.
Yeah.
Let's stick Gus on.
Can you help me? No,
I want to get a bag.